So today we are covering mixed models, mixture models. Oh, I'm sorry, man, I keep forgetting to update my titles. But yeah, we're covering mixture models today. And these models are combinations. So effectively what we're going to do is we're going to take some of the models we've already learned and combine them with other distributions to create sometimes two-stage models, to create models with extra parameters that adjust for various features of real-world data, right? I mean, a kind of key feature of applied statistics is that the data we're working with rarely conform exactly to the features of the likelihoods that we're using, right? There's often some feature of the data that doesn't exactly fit. Um, and so today, the kinds of models we're going to look at combine features from multiple different likelihoods to better approximate the real features of the data we're working with. And the typical case here is that we have some outcome that is caused by multiple processes, not just a single process, right? So we might have a count process that follows a Poisson distribution, but we might have a situation where there are multiple processes at play that are driving that count, not just a single process. So we'll start with what I think is the simplest example of this, which is over dispersion. So over dispersion, well, first let's kind of start with the Poisson model again. So the Poisson model, right, has a single parameter lambda. This little Greeky thing is lambda. Um, and a key feature, the defining feature of the Poisson model, is that the expected value of y and the variance of y, our outcome, are both equal to lambda, right? So we have a mean variance equality in the Poisson, right? So as the expected value of a count increases, its variance increases, but its variance is exactly equal to the expected value, right? This is the defining feature of the Poisson distribution. And just as a reminder, here's what it looks like in practice. With the lambda equal to 1, we see, and this is the same slide from last week, with a lambda equal to 1, we see that most of the mass is concentrated on 0 and 1, and the distribution is relatively tall and narrow, right? But as lambda increases, the peak pushes down, spreads out, right? So 2, right, the mass moves a bit away from 0, but also spreads out. 3, when we get to 9, we have a distribution that is quite spread out and quite low in peak, right? So its expected value is 9, but the mass is spread out around that. And so this is what happens with Poisson as we kind of move away from 0, the distribution becomes shorter and wider, right? And everyone talking about flattening curves these days, they want to push that lambda out, right? And they want to spread that distribution out and lower the peak, right? So that's actually the kinds of models that people are using to forecast these things. Over dispersed models, though, right? And we'll get to those in a second. Okay, so as lambda moves away, it spreads and flattens. And that's pretty typical for most count outcomes we see in the world. However, that expectation of the variable equal to lambda and the variance equal to lambda doesn't actually accurately describe a lot of real world count outcomes, particularly social count outcomes. So a lot of times we have a phenomenon known as overdispersion. And overdispersion occurs if the variance exceeds what is expected by the model, right? So if the variance is greater than lambda, we have overdispersion. An account in a Poisson, right, is when the variance is greater than lambda. In a binomial, it's overdispersed when the variance exceeds np times 1 minus p, which defines the variance for a count binomial model, right? Remember that for a Bernoulli, the variance is p times 1 minus p, and in a count binomial model, we just multiply that by n. Okay, so we have, the overdispersion is a phenomenon where we actually have more spread than what we see here, right? That we expect a 9, but our variance is actually greater than 9, right? So we're going to return to that fatal encounters data that we used a couple weeks ago. It's in your root directory as FE demo if you want to follow along. And what we're going to do is so these are county level data by race of men's deaths, men killed by police. We're going to aggregate those to just make a single count per county, so it's not by race anymore. It's just total deaths and total population for Latinos, African Americans, and whites, right? So we have the sum of those three populations and the sum of the deaths from those three groups. That's adult male population for those three groups and total adult male deaths for those three groups. And so what I want to do is create an intercept-only model to predict out county death rates, right? So we're going to use our offset Poisson model again, where we're going to let the deaths in a county be distributed Poisson with a parameter lambda, where the logarithm of lambda is equal to the logarithm of the population plus some unknown parameter alpha, which we're putting a prior of normal 0, 2 on, right? So each county, right, is going to have a prediction that's structured by alpha and by its population size. So we're effectively going to get deaths per, we're effectively modeling deaths per population, a count of deaths per person. And here's the model we'll use, right? Remember that offset term can be added very simply by just adding the log of the exposure variable onto the right-hand side of our linear predictor. Any questions about the setup on this? This is review, but I'm happy to take questions if anyone's confused about how I set this model up.
So would we follow a similar, because part of the homework exercise this last week was comparing QUAP versus ULAM and so forth. How would that be different here?
So I'm using Ulam. QUAP, remember, the, the point of that exercise in the homework was to show you the limits of quadratic approximation, right? That when our posterior is not approximately normal, then QUAP is going to give different inferences than MCMC, which is what Ulam does, right? So QUAP is
Okay.
using,
Yeah.
right, an algorithm that basically takes the gradient, takes the second derivative at a particular point and looks at the curvature at that point, and then estimates a normal curve that describes that particular point, and then kind of estimates the posterior from that, assuming approximate normality. But if our posterior is not approximately normal, then MCMC is going to give us better inferences. That's not
Okay.
typically a step that I think you need to worry about. That was a homework exercise that, if you wanted to be clever and think about where quadratic approximation fails, if I were an instructor, that's the sort of thing I would assign for you to do, is to take a real world example where I expect a posterior that's not approximately normal and then compare results on that. I mean, the other benefit to QUAP is it fits, immediately. You don't have to run a model through Stan. So it's fine to just, test your model there to get it working. And then when you have it working, run it through Ulam to run MCMC, because those can take a little time. Other questions?
One last question. We don't need to do anything weird to population, like standardize it or anything like that. Okay.
No, in fact, you shouldn't, right? Whatever you do, then you're effectively turning that into the unit for comparison. So one thing you might do is make it population in hundreds of thousands, right? So that way my model is on the deaths per 100,000 scale, or the deaths per 1,000 scale, or whatever ultimate scale you want to use, but I can easily make that transformation outside of the model as well. Oh, I think Dorothy wanted to tell you. What is it?
No, I want to tell you something.
What is it?
The,
What? Okay. Well, that's fine. Are you asking me to get it? Yeah. Okay. I have to get a Pokemon book for my daughter real quick. 1 second. It's super deluxe. All right. Go enjoy that.
You want to see, Dad?
So if you wanted to know about the second evolution of Bulbasaur, that's your book. Okay. Dorothy's really into Pokemon right now. It's cute. Okay, so where was I? Offsets, rates, right? We had this conversation when this came up initially. Yeah, so you can make those adjustments inside or outside the model, right? I think including the offset in the model when you have one makes a lot of sense. And it certainly makes the model a little easier to interpret, and it makes your posterior a little easier to interpret. Okay, so other questions about this model? pretty simple Poisson model, right? We don't have any predictors in it, right? We're just estimating a single intercept for the country, and we're saying all counties are basically the same. The only difference in it is population size, right? So we do expect lower counts. What the model's saying is, yeah, we expect to see lower counts in small population counties, right? We expect to see higher counts in high population counties. That's what that log p is going to do. Is it's going to adjust the model up and down based on population size, and then it converts it in effectively into a rate model. Okay, cool. Now, I estimated the model with Ulam there. So I'm going to do my typical, setup to pull posterior predictions. In this case, I am just going to directly simulate for a hypothetical county with 100,000 people, right? So the only variable in the data is pop. So I'm going to set up, let's say we have a county with 100,000 people. Draw me 1,000 simulations from that county, right? So 1,000 predicted death counts from that county. And then I'm going to take my observed data. That's the actual observed deaths from each county in the country. I'm going to convert those into deaths per 100,000, right? So I'm going to divide it by the population and then multiply that by 100,000. So that way I have my deaths in a county with 100,000 people over here and observed deaths per 100,000 population over here, right? And so these are on equivalent units and they're comparable. Then I'm going to set these up as a data frame real quick, where I'm going to take the variance of my observed and the variance of my simulated, and the mean of my observed and the mean of my simulated. And what do we got, right? My mean isn't too far off, right? I observed a mean of about 5 deaths per 100,000 people across U.S. counties. So the average county, if it had 100,000, has a death rate of about 5 men killed per 100,000, and this is over 6 years, so it's kind of wonky. It's 5 deaths per 6 years, 5 deaths per 100,000 per 6 years. And the paper, we normalized that to a single year, right? And that's where I would kind of use just math to regularize, to convert that into a unit that makes sense after I've modeled it. But the model predicted 5.36 deaths, right? So slightly higher, but not dramatically higher. But where we have a big problem is here, right? The variance in the observed data is just wildly higher than the variance that our Poisson model expects, right? The variance in the observed data is 131, and the variance that our Poisson model is obviously equal to that lambda parameter. So we have about a 5.4 lambda, right? And in this case, lambda is equal, log lambda is equal, so lambda is equal to e to the log p plus alpha. So e to the p plus alpha. Anyway, okay. So plus e to the alpha. So here, we're going to compare the model predictions to the observed data just to see what this looks like. So this is one way to think about it. Here's another way to think about it. This is the density of our posterior simulations in the top panel, right? So this shows our Poisson model predictions in terms of death counts, death rates rather, deaths per 100,000. We can see, right, it ranges between 0 and 10. The bulk of the mass is around 5. This is our observed on the same scale, where I truncate the x-axis to only go to 0 to 15. And we can see that the tail is really long, but we also have a bunch of bulk at 0, right? A bunch of counties report no deaths. And this is what it looks like when I don't constrain the axis. So it's the same data, but I just let it go out as far as it'll go. And we have some counties that report like a 200 plus mortality rate. And those are very small counties that had 2 deaths, which translated to an incredibly high mortality rate. And then a bunch of counties with 0. But those tails are really long, right? Which that variance is really high, right? So the Poisson model kind of pushed the center out too far and made the tails too short, right? The tails are not big enough and the center's pulled away. And this data is over dispersed, right? The variance on it is way higher than what the model expects, dramatically higher than what the model expects. Everyone with me on kind of what this over dispersion phenomenon means, right? We have here a lot more variance in our count than we expect if the process was truly a pure Poisson process, right? We have a variance of 131 instead of 5.4. We're getting the mean right, our model's getting the mean pretty close to right, but it's really missing the mark on the variance. Okay. So over dispersion, which is what we're seeing here, results from mixed processes when outcomes have more than one cause or are a sum or product of processes, right? So in the case,
Dad, I found out that Pokemon, all some Pokemon have like, you know how like, you know that there's a mega, you know what,
can you tell me about this when I'm done teaching?
what Wadia is? It turned into a mega.
Cool. So she's learning all kinds of new and important things. We are engaged in high quality pedagogy here, homeschool. Really, we're covering the basics of biological taxonomy. We're doing a good job, I think. Okay, so overdispersion results from mixed processes when outcomes have more than one cause or a sum or product of processes. So in the case of like police killings, right, we have a lot of different things feeding into this. We have, baseline population characteristics. We have police department characteristics. We have various historical processes. There's a lot that causes a police killing to occur, right? It's not just a random feature that occurs at the same rate across different places, right? And so all of those different processes are kind of feeding there to be some places with really low counts, some places with really high counts, right? And those are kind of pushing the distribution out or in different ways that our model doesn't currently observe. Now, most count variables are overdispersed. I said this already, but you should assume overdispersion, right? I have never seen a social process that was perfectly Poisson distributed. I've never seen it, and I don't think that there is one. The Poisson distribution describes like astronomical phenomenon really well. It describes a lot of natural process as well, but for social processes, it's just about always going to understate the variance in the outcome. So assume that your variable's overdispersed, and it turns out not to be that costly to do so. It's not that much more complex to model an overdispersed outcome. But failing to adjust for overdispersion leads to dramatic overconfidence and posterior inference, right? Here's our 89% interval for death rates, right? Between 0.5 and 9, right? When the actual 89% interval of the data is between 0.1 and 75, right? So we're going to overstate our certainty. We're going to dramatically understate our uncertainty if we rely on a regular Poisson model when we have an overdispersed outcome. And what this means in practice, if you've seen papers using regular Poisson models, or if you've ever run one, is if you run a frequentist Poisson model, just about every predictor in your model will always come up significant, right? Because your confidence intervals are often wildly too narrow, right? And in a Bayesian context, your percentile intervals will be far too narrow. And so you'll have more certainty about the location of your parameters than is warranted by the data, right? And so typically in statistics, we like to err on the conservative side. We like to say that there's more uncertainty than there actually is, rather than saying there's less uncertainty than there actually is, right? Being too liberal about your uncertainty is a bad thing in statistics. You always want to try and be conservative. So assume overdispersion, right? There are some tests you can use, but I don't think it's typically necessary. Again, if you're modeling a social process, I can guarantee you it's overdispersed because we have complex causation for just about every social process, right? There's very few things that are driven by a single Poisson process in the social universe. Okay. So again, if you see someone with a Poisson model and they're like, these effects are statistically significant, you can say, well, did you adjust for overdispersion? And if they do, it might not look so rosy for them. But also, we're not doing statistical significance anymore, so we can kind of, dispense with that anyway. Okay. So how do we address overdispersion? The book presents two approaches. We can use, there's a variety of approaches we can use. The book presents us with the negative binomial model, typically called the negative binomial model. Here it's also called a gamma Poisson. and there's also a beta binomial model. So it depends on the kind of outcome we're tracing. If we're tracing a Poisson outcome, right, where the probability of the event is relatively rare, as in the case of a police death, right? Police deaths, and for men are about 2 per 100,000, and for the whole population are about like 0.8 per 100,000. That's a pretty rare event, right? The probability is like 0.0001, right? And so we are more zeros than that. 5, 7 zeros. But yeah, very rare event relative to the population. Obviously, subgroups have higher risk than others. So if we have a low p and a high n, a Poisson is the appropriate likelihood to use. If we have a p that's relatively higher, then a binomial count model is more appropriate, right? The shape tends to work better. But we also often have overdispersion in binomial counts as well, right? And so beta binomial is another approach we can use. I'm not going to cover beta binomial today. I actually think there's a bug in the software. I wasn't able to replicate the results of the book. And I doubt maybe one of you can for the beta binomial demos. But my MCMC algorithms were not working. The chains were not converging at all for those models. So I don't know if there's something wrong with the software or if it was user error. But not going to demo those today. They're cool. I've used them before. They're really neat. They require a little more work on your part to set up. Negative binomial is pretty common though, and so we definitely will cover that. So a negative binomial is a model we can use to adjust for overdispersion in our counts. Now, when we get to multi-level, I'm going to show you a way we can use multi-level models to adjust for overdispersion in a way that's theoretically analogous to what we're going to do with a negative binomial or a beta binomial process. What we're effectively doing is we're saying that each observation of the data could have a variance or a rate that's a little higher than the baseline in the population. We're effectively allowing each observation to kind of bump itself up a little bit. We're kind of adding an error term into our model, right? And we can do that very easily with a multi-level model by adding intercepts for each observation. Here we're going to do it with a parameter in the likelihood, but later we'll do it with a multi-level model. And in practice, that's how I model overdispersion, is with a multi-level approach. Okay. So we'll get there. So I'm going to teach you this. This is an approach that's appropriate for non-multi-level models, but when we get to multi-level models, we can solve this really easily there too. You'll see negative binomial a lot though, so it's worth learning. So we're going to allow for unmeasured variables to influence counts, and we can let each Poisson variable have its own event rate, right? So we have lambda, but we can also allow the variance of each count to move a little further than it would just according to lambda alone, right? And so we're going to have two parameters now. Each row of the data is going to get a lambda, and it's going to get a phi, right? This one is a phi. And phi is going to determine the dispersion of that count, right? How variable is that count expected to be? So what we use to estimate phi is a gamma distribution, right? And if you recall, the gamma distribution takes on non-negative values, right? So it has a shape that is kind of skewed. It's based on the gamma function. So it's skewed and it's constrained to be non-negative. So it's really good for modeling rates, right? Rates of an event can't be negative, right? They're constrained to be non-negative. So gamma is a great distribution for modeling that. In the context of the beta binomial, the beta distribution is constrained to be 0, 1, and is often used to model probabilities. So the beta binomial model allows each observation to have its own probability of event occurrence, which captures that overdispersion as well, right? Effectively, we're allowing there to be kind of more wiggle in the data than our model would ordinarily let there be. We're not really capturing that unmeasured variation formally by saying here's a predictor that could capture it. What we're doing is we're just saying, hey, model, there's extra noise here, and we want you to be flexible enough to allow that noise to adjust your predictions. We effectively want that noise to be baked into our model so that we capture uncertainty more accurately. So our dispersion parameter phi is going to give us extra variance. Oh, Missing a sim there. Sorry. So DI is distributed negative binomial. Fix my typos as I go. Next. There we go. Yep. Missing it. Okay. And I cached all my models, so it should compile pretty. I'll push the corrected changes up at the end of lecture. Yeah, I think I showed you this in lab, but it's a good idea when you're running Ulam models and you're doing a markdown to cache the results, so that way you don't have to recompile the models every time. Okay, cool. So D is the deaths are distributed negative binomial, right? So before we distributed the deaths Poisson, right? Now we're going to distribute the deaths negative binomial. And again, negative binomial is analogous to a Poisson with that extra dispersion parameter, where the counts can be a little more variable than they would under a Poisson, or a lot more variable depending on the posterior for phi. Okay, so the linear model is going to be exactly the same as we've used, right? We're still going to use the log link, and I'm still going to use my offset term just as I had before with a single intercept. Same priors, but now I need to add a prior for phi, and I'm going to use an exponential one, right? The dispersion is constrained to be positive. Variance has to be positive, right? So I want to use a prior that makes it positive. I could maybe, so if I take an exponential lower than 1, it actually gets fatter tails. And in this case, I might want to do that just to allow the prior to have more space for fat tails. In this case, I've got a lot of data, so the prior is going to get overwhelmed anyway. Okay, here's how I estimate it. The likelihood is called gam-Poisse in rethinking. So I can use dgam-Poisse to specify, remember, because it's a mixture of a gamma and a Poisson process, where phi is effectively following a gamma likelihood, and lambda is following, is kind of driving a Poisson process. Okay, so same model here as we had before, but now I have this extra phi parameter and a prior for phi. Yeah? So nothing too surprising here. Now here's what we look like. These are the posteriors, so I just did extract samples here so we could look at it, right? So for alpha, right, which is just our count intercept, which are both on a log link with the offset, so they're comparable in terms of their interpretation, right? Those densities look really, really similar, right? Their shape is very similar, but the range is indistinguishable, right? So what they're saying is the expected value for our death count in both the Poisson and the negative binomial is the same, right? The expected value, the mean of the distribution. And we saw that our Poisson did a pretty good job of capturing the mean in the first place, right? But here's our phi estimate, right? And this, again, captures over dispersion. If you want to see how it's parameterized, it's in the book. You can kind of work through exactly what this phi parameter means in terms of dispersion. But we can see that the model says, yeah, there's definite over dispersion in this parameter, right? The estimate for phi, right, ranges between 2 and 3.25 or so. So we have some over dispersion in this model, and that variance is going to get added into our expected counts. So let's look at what that looks like. I'm going to simulate from it. So I'm going to take draws from my Poisson and draws from my negative binomial, where again I'm just saying 100,000 people, right? Give me 1,000 predicted death counts for a county with 100,000 population, right? And I want to set this up so I can look at the three together, right? So here's my negative binomial predicted values. Here's my observed values. And here's my Poisson values on the right, right? So negative binomial, observed, and Poisson. So the Poisson, remember, was peaked away from 0 and had really skinny tails, understated the variance. The observed is peaked at 0 but has really long tails. Now the negative binomial pushes some of that weight closer to 0 than the Poisson, right? It shifts it a little bit. But notice those tails are a bit longer. So when we're at about 10, we get similar values at 10 here, but it kind of falls off a bit lower, and these tails capture some of the features of this shape that extend longer, right? So it's still not perfect. They're still kind of clumping at 0, that we see in the data that the negative binomial isn't capturing, but it's doing a better job than the Poisson, right? There's more variance in these negative binomial simulations than there is in the Poisson simulation. So there's still something about, a lot of zeros in these data that we're not capturing particularly well. We maybe need a more intricate model to do something about that. And what I think is going on here is that for counties with small populations, we just don't have enough data to really to observe events in those counties at this point because the event is rare enough that we didn't observe it. But we could have a process. We could have a zero inflation process going on too, which we'll get to next. Okay. So negative binomial here doesn't solve all of our problems, but it does a better job, right? It does a far better job of kind of returning the observed data than the Poisson does, right? These tails are kind of capturing, some of the width in these tails is a little better than the Poisson, where effectively the probability of observing a 20 in this model is 0. Here, it's not, right? Here, we could observe extreme values. Here, we just can't. Questions? Everyone feel good about over dispersion and what it is? And if you're running a count, you should always address it. Unless you're like a biologist or an astronomer or something. And even then, maybe astronomers probably don't have to worry about it. Biologists might. Okay, cool. Let's move on. Zero inflation. Now, I'm not going to actually use the fatal encounters data anymore today. I'll explain why now. Sometimes we have multiple processes going on in count models, right? Now, we could have, in our count model, process A that determines whether the event occurs at all, and B, if it does occur, determines how many events occur, right? So we could have a binary process, yes, no, the thing happened. And then a second process, how many events happened, right? And if we have that set up, then we have the possibility of observing more zeros than we would ordinarily expect from a count model, right? Because we're going to see a lot of cases where the event never even started, right? The process that leads to a count never even started. Now, I don't use it for these data, even though we observe a lot of zeros, because there are police in every U.S. county, right? There is a possibility of a police death in every U.S. county. Now, if we had counties where there were no police, then a zero inflated model would be totally appropriate. If there are no police, there are no opportunities for people to be killed by police, right? But that's not exactly the process we have here. So we need to have a situation where there are cases where the event may not have occurred, right? And it's not just, it may not have occurred because of the sort of ordinary structure of a count process, which can give us zeros, but it may not have occurred because something else didn't set the event to go off in the first place. So if we're counting salamander populations in a forest, for example, for those of you who worked the homework example, those ordinary ecological variables could determine population counts. And sometimes we're going to see zeros because of those processes. But there could be something else that goes on, like, I don't know, upstream there was a toxic, some pollutant that was dumped into the watershed that got into the stream, and salamanders are very sensitive to pollutants, and so all the salamanders died, right? And so any place where we have pollutant exposure will never have salamander populations, right? And so there, if we don't adjust for that pollutant exposure process that's going to determine whether or not salamanders can even possibly live in this place, we're going to underestimate the number of zeros that we're going to see ordinarily in the data. That wasn't actually occurring in the data that you had, but it's certainly a possible outcome. The book describes, you could count the number of birds you see at a bird sanctuary one day, but maybe, you honked your horn on the way in and scared off all the birds, and so there were no birds that day. But that's not an ordinary part of the process that determines how many birds are in that place, right? There was some other event that that reduced the count to zero for a different reason, right? So we want to think about this as kind of, is there a second process that turns the event on or off, right? Is there a binary logistic event that turns the event on or off? So we have two components in a zero inflated model. we have a model describing the probability that the outcome is 0, and we have a model describing the expected event count, right? And regular count models also produce zeros. So what this model is going to do is it's going to take the zeros that we already observed and add more to them, because it's going to say that there's some observations that have a higher probability of being 0 than others because of this second process that turns the event on or off. So here's some zero inflated count outcomes that we could imagine. The number of snow days in a school district. Can anyone think of why that might be zero inflated?
There might be other reasons why school is canceled. I don't know.
So we're going to say they're exclusively snow days. I'm thinking geographically here, right? So New Jersey might, like the number of snow days annually might be, a Poisson process. We have to adjust for increasing average global temperatures to put a downward time trend on that, sadly. But what else could be going on? How many snow days you get in Florida? Right? So how many snow days you get in southern New Mexico, right? So there are some places that are just never going to observe snow days, right? And we could imagine a process where there are particular climates in which it never snows. And so we need to adjust for that to accurately model the number of snow days across all US school districts. Some of them will always be 0, right? Some of them will have a Poisson count that's determined by the weather that year. That's random, right? Okay, prison admissions in a county. Similarly, there are some prisons with no counties, right? So some are going to have, high levels of it, are going to have Poisson numbers of admissions. Some are going to be 0 because they have no prison. And some are going to be 0 because there was no one admitted to prison that year, although I don't think that actually ever occurs. But, we could imagine there being a 0 admission year in a prison when there was, in fact, a prison. And then obviously, if there's no prison, there's always going to be a 0. Well visits to a doctor per person. And want to think about why this might be 0 inflated?
Well, people don't go to the doctor.
Some people don't go to the doctor, maybe because they don't have health insurance, right? They may not have access to medical care, so they just don't go. Or they're, just stubborn. But I will use a class-based argument to explain that. So well visits to a doctor per person, right, are going to be largely a function of access to medical care. If you don't have, coverage for well visits to a doctor, you're not going to go. So there's a 0 inflation there. We need to adjust for the fact that there's a portion of the population that is actually kind of going through a different process. For the rest, it may follow that Poisson count where the expectation would be you go once a year, sometimes you go more than once a year. Okay. Sometimes you don't go at all. Okay, so we're going to demo this with, I don't know how many of you have seen the IDRE at UCLA. They have a really good set of stats walkthroughs. Their page has a lot of demos in R and Stata and SAS for how to run different kinds of models. So it's a nice resource. And they also have a lot of demos for different kinds of models. In this case, they have a demo on 0 inflated models that works through event counts for fish. I thought this was better than the monks writing manuscripts example because that's just all simulated data. I'd rather work with real data. Okay, because I'm stubborn. So we're going to read in this data off the web, and then we're going to pull out 4 variables from it. Persons, camper, child, count. So we're effectively asking, you went on a camping trip, and each group was asked as they left the park, say a state park with a river in it, how many fish did you catch, right? And so count is a measure of how many fish that group caught. Persons is a measure of how many people were in that group. Camper is a measure of whether they had an RV. Child is a measure of whether they how many kids they had in the group, right? So I'm going to suggest that people in big groups and groups with kids are less likely to go fishing, and the people most likely to go fishing are people who are camping alone. I don't know if that's right, but that's what I'm going to go with. So what we're going to do is we're going to think about whether there's a systematic difference in these groups, whether some groups were less likely to fish at all, right? And then among those who did fish, what was the expected count of fish they caught? right? So we're going to build a model that's going to simultaneously account for the probability that they fished at all and how many fish they caught. We're going to allow for excess zeros, right? We're going to allow for 0 to be higher than it would be if we had an ordinary count model. Okay, so if we assume that the average person who goes fishing catches 2 fish, so we're going to make a Poisson with a lambda of 2, right? Then this is the distribution we get. I'm going to simulate that. So I'm going to just say we had 250 rows in the data. I'm going to draw 250 observations from a Poisson with a lambda of 2. And then I'm going to plot those against each other. So the pink is the observed data, and the green, bluish green, is the Poisson data, right? And we're capturing the distribution not terribly at kind of this range, but notice we're missing a lot of zeros here, right? And that's because a lot of people just didn't go fishing. Among those who did fish, lambda might actually be higher than 2, right? Because we see these kind of tails here. So we might actually have a process here that's both zero inflated and over dispersed. I'm going to show you a zero inflated Poisson, but we might actually want a zero inflated negative binomial here, which we can do, right? If you can imagine it, you can do it. It just takes more work. But in effect, what we're going to do in this model is we're going to run a logistic regression first. First, we're going to run a logistic regression on is the count of fish equal to 0, right? So we're first going to run that logit model to estimate the probability that the count of fish you caught is equal to 0. After that, we're going to run the Poisson model that estimates the count of fish. And we're going to add the probabilities of zeros obtained from both of those models to inflate our count of zeros up, right? So it's a 2-stage regression. First, we're going to run this logit model that says that the probability that you didn't go fishing, here we're kind of inversing it. Ordinarily, we're asking the probability that the event is true. Now we're asking the probability that the event is not true, is equal to some intercept plus some beta times the number of kids you had with you, plus a beta times the number of people you had in your group, right? I'm assuming people who just went to hang out with their kids and went to go sit around a campfire and make s'mores were less likely to fish, right? So again, first the logistic regression, and then the Poisson regression, right? The log of the expected number of lambda, the expected number of fish, is a second alpha. So we have alpha p here and alpha L here, 2 different alphas, 2 different models, 2 different linear models here, right? And we can change the variables that are in them. Notice I don't have kids in the second stage of the model. I just have people. Because I think maybe there's 2 processes. One that's like, okay, if you're with a big group and you have kids with you, you're probably not going fishing. But if you do go fishing and you have a lot of people with you, you're definitely going to catch more fish, right? Because more people just means more fishing rods, means more fish. So I can actually have the same variable going in different directions in this approach. Because I can have it going in one direction for the logit and another direction for the Poisson. Now, again, that's just my theory. I don't know how it's going to shake out when I estimate the model. But that's my theory, is that people should push in 2 different directions here. There should be a baseline decrease in probability of going fishing if you have a lot of people. But if you do go fishing, you're going to catch more fish because you got more rods in the water. Okay. So this is the monster of a model, right? It's big and it's a bit ugly, but we can do it. So the number of fish you catch is 0 inflated Poisson. Now I could easily make this 0 inflated negative binomial, but here we're going to stick with Poisson. The logit, so this is my logit model, right? Is what I just walked you through. Here's the Poisson model, and here's my priors for all my parameters. So I have alpha p, beta 1p, beta 2p. That's all the priors for my logit model. And I have alpha L and beta 1L for my Poisson model, right? But every parameter gets a prior, and here we have 2 linear models, so we have double the parameters. So we're getting into a lot of priors here. But that's okay. Here's how I estimate it. I use the dzi Poisson, right, which is the density function for a 0 inflated Poisson. We're getting close to the point where you so McElrath actually wrote custom likelihood densities here, and we could use the math to do that ourselves too, right? So if I wanted to do a zero inflated negative binomial, what I would have to do is program the math for the zero inflated negative binomial density function, which I could find, a math textbook, or I told you Wikipedia's statistics pages are really useful. They actually have the cumulative density function and the probability mass function for the zero inflated negative binomial described. So I could just program that in R, and then I could make a function out of it, which I'll show you how to do in lab on Tuesday. We'll do user-defined function. Okay, but then I have two now. Instead of one, I have two linear predictors, right? I have the logit and the Poisson piece, and then all my priors. And I estimate it as I would any other model, right? The only difference here is I have two linear predictors and a whole bunch of priors. Yeah? Everyone kind of following this? We're good? Okay. Thank you. Here's the model. Okay. So the beta 1 is attached to kids. So groups with kids are less likely to go fishing, right? Because that's higher than 0. Groups with lots of people are actually more likely to go fishing. Remember, we're estimating the probability that it's 0 now. And then, anyway, this gets really hard to interpret. I keep telling you, don't really focus on the parameter estimates, the posterior means. We really need to flip over into predictive territory to understand these models well. With mixed models, that gets even more important because these get very difficult to read. But I do want to look at this just to see, okay, my effective sample size is good. My R hat is good. I could look at the trace plots to check convergence. So these estimates are probably trustworthy. Okay. But in this case, what I would ordinarily do is then run this through a simulation to check my expected counts of fish, just to see if I could retrodict the data, and then think about the relationship between the number of kids and number of people. But here we do see, right, a positive value on that person's. So we do expect that, as more people join the group, you're going to catch more fish. The probability that you're going to go fishing decreases with kids, but increases with larger groups. Yeah. So zero inflated models are tricky, but powerful. Any questions on the zero inflated models? Probably many. Here, again, the goal is to kind of add things to your toolkit. I'm not expecting you to have mastered these yet, but I'm expecting you to, when you see them, know what they are. And if you encounter a problem that you think fits this description of like, okay, it's a count and it's a social process, so it's probably over-dispersed, I should consider an over-dispersed model. Or it's a count and there's probably multiple processes going on here that trigger it on or off, so I should consider a zero inflated model. I want you to recognize the kinds of situations that this would be useful for, and I think now you probably know enough to poke around and figure out how to use them on your own. Okay, all that said, questions? Okay, let's take 2 or 3 minutes. We'll start again at 10:56. All right, so statistics. Ordered categorical outcomes. This is going to be our last topic for today. We covered multinomial regression last time, right? Multinomial regression is appropriate for unordered categorical outcomes, right? So if we're trying to capture the probability that a categorical outcome is in group 1 relative to group 2 relative to group 3, but there's no inherent order. There's no inherent order to the variable, like, for example, a U.S. state, right? We might think that some states are better than others, but there's no inherent rank to them. But ordered categorical variables have a clear sequence or ordering to them, and we encounter these a lot. Likert scales are the most common, that range from 1 to 7, strongly disagree, all the way through strongly agree. Passenger class, right? For example, on the Titanic or on an airline, right? These are ordered, but they are categorical, right? Where we could argue that the distance between economy and business and the distance between business and first class is definitely not equivalent, right? That jump from business class to first class is way bigger than that jump from economy to business. I don't know. I don't know. But school grade, maybe like the jump from kindergarten to first is kind of qualitatively and quantitatively different than the jump from, say, like eighth to ninth grade, right? That there's like more of a change. It's not just that the gap between each grade is a linear increase, right? We can't just draw a straight line between, the I don't know, difficulty and rigor of each grade, right? There may be qualitative differences in that. In the same way that there might be qualitative differences in educational attainment, right? In terms of maybe the social value, in terms of the probability of attaining them, in terms of the difficulty, in terms of the accessibility, right? That the jump between less than high school and a high school diploma might be way less than the jump between a college degree and a graduate degree, right? I don't know. But these have an inherent order to them, but it's difficult to say that there's a linear, relationship. So a lot of times what people will do is they'll turn these, especially these Likert scales, into a numeric variable and just model them as a integer or as a real number variable, right? The problem there is that we assume that the gap between 1 and 2 is equal to the gap between 6 and 7 if we treat it as strictly linear. And our predictive scales are going to get a bit wonky, right? So if we use a Gaussian or normal process, right, we can predict negative values. We could predict a 1.3, and what does a 1.3 mean on a discrete 1 to 7 scale? We can run into all kinds of little issues with this. So we kind of the way we kind of describe this distances problem is an assumption, right? That we make if we use a numeric a real number scale to translate these ordered categorical variables into a real number scale, we're assuming symmetric distances between ranks, right? And that is an assumption that is often invalid, right? For example, if I ask you, how much you like mustard, right? Some people, the distance between like a 5 and a 6, it's like, yeah, I like mustard, right? But the distance between like a 1 and a 2, right? Like I hate it versus like, I don't like, it's not my favorite, right? The distance between I hate it and it's not my favorite is probably bigger than the distances between like, I like it 5 and I like it 6, right? So we or the distance between like I like it 6 and I like it 7 might be greater than the distance between I like it 3 and I like it 4, right? People don't necessarily make these rankings in a way that is consistent with just that linear approach, right? There's all kinds of jumps and gaps in there that are structured by preferences and by other processes that kind of push these things in different ways, right? We don't set school grades up to be an exactly linear process. Okay. So here we're going to do some more college admissions, graduate school data. How likely are you to apply to grad school, right? And we should rerun this survey in the midst of a global pandemic. But again, I'm going to use IDRE from UCLA's sample data on this. And we have a kind of compressed Likert scale here, right? A 0 means I'm unlikely, a 1 means I'm somewhat likely, and a 2 means I'm very likely. Right? And so this is an ordered categorical outcome, right? We don't want to model it just as 0, 1, 2 on a linear scale, because the difference between I'm unlikely to apply and I'm somewhat unlikely to apply, or somewhat likely to apply, is probably vast, right? Those who are unlikely to apply are probably people who just like have never considered it. It's not on their radar at all. Those who are somewhat likely and very likely are probably more similar, right, than those who are unlikely and somewhat likely. The jump between somewhat likely and very likely is probably smaller than the jump between unlikely and somewhat likely, right? There are those people who are just not considering it at all, and those people who have given it a thought, and those people who are definitely doing it. So is the distance between each of those symmetric? I'd suggest it's probably not. Now we're going to ask whether GPA helps us understand whether graduating seniors are thinking about applying to graduate schools. To think about these, we need to think about so the way this model works is a little different, right? An ordinary logistic regression model, and we're going to use a logit framework here. In an ordinary logistic regression model, we're predicting the probability that you are a 1 or a 0, right? So we have a probability scale. But here we have a lot of possible outcomes that occur in a sequence. So the multinomial model, the categorical model, also has multiple outcomes, but it doesn't really care what order they occur in, right? So we'll have the probability that you're in this group and not this group as our kind of reference, but the reference is arbitrary. And we don't really care about keeping them in order as we predict and model them. But here we do. And so implicitly what we want to do is we want to have a 0 to 1 probability, because you got to fall in one of these groups, but we're going to put cut points on this probability distribution that says if you fall in this range, you're in group 1. If you fall in this range, you're in group 2. And if you fall in this range, you're in group 3. I'll show you what this looks like. What we're doing is we're translating our regular probability into a cumulative probability, right? So we're effectively saying you must belong in one of these 3 groups. Now we're going to start at 0, unlikely. We have 220 out of our 400 observations that are unlikely to, let's say they're unlikely to apply to graduate school. That's 55% of the data, right? So I calculate a proportion by just dividing the number in this category divided by the total number of observations. But I'm also going to calculate the cumulative proportion. So up to this value, how many do we have? Up to 0, we have 55%. Now let's move to somewhat likely. 35% of the sample says they're somewhat likely to apply to graduate school, right? But the cumulative proportion that say I'm either unlikely or somewhat likely is 90%, right? So now we actually already know how many are very likely to apply. Why? We don't even need to compute this final.
Because you just subtract 100% minus what has already been captured.
That's right. So that's effectively the law of total probability, right? The probability of an event must sum to 1, right? So if we have a binary context, the sum of the event and not the event must be 1. If we have 3 categories that are mutually exclusive and exhaustive, meaning all they must, one of these categories must occur and 2 events cannot occur, then it's going to sum to 1, right? So once we know 0.55 and 0.9, we know that 0.1 are in the very likely category, right? So what we're doing is we're effectively kind of making a stair-step model. We're saying that if your P is up to 0.55, you're in the unlikely between 0.55 and 0.9. You're in the somewhat likely category in between 0.9 and 1. You're in the very likely category. So this is the proportions, right? Just the regular proportions. And this is the cumulative proportions, right? So we have here just regular proportions, 55% unlikely, 35% somewhat likely, 10% very likely. But when we translate it to cumulative, you can see that when we're at the final category, we're at 1, right? And this cumulative process is what we're going to use as our link function here. We're going to use a cumulative logit process to basically let us model the probability that you're in group K, but we're going to estimate that probability that you're in group K by differencing the probability that you're in group K minus 1. And because we're doing this cumulative model, once we've made that difference, we've also differenced out the probability that you're in group K minus 2 and K minus 3 and K minus 4, right? If we have a bunch of different outcomes. What this looks like in practice, right, is that we're going to estimate the probability of group 1 as just a baseline probability, right? In this case, group 1, the cumulative probability that it's in group 1, unlikely, is 55%. It's just its baseline proportion, right? But the probability that you're in group 2 is going to be Q2 minus Q1. So it's going to take the probability that it's going to sort of increase, or it's going to take the cumulative probability that you're in that group and difference it from the probability that you're in group 1. And then it's going to take the cumulative probability that you're in group 3 and difference it from the cumulative probability that you're in group 2. So we get effectively the regular probability, but by treating it as cumulative, we ensure that the order stays fixed, right, as we model it and as we predict it out. These are complicated models. They're difficult to grasp and difficult to use, but we're kind of working on, effectively, we're estimating k-1 separate logistic regressions as we did with the multinomial or categorical model. But now, because we're using this cumulative link function, we're fixing the order they're in, right? Where the reference group is not arbitrary. The reference group is the prior group in sequence. And we use this cumulative probability to ensure that they stay in the right order. With the ordinary categorical model, it doesn't matter. Any group can be the reference. Here, it very much matters, and the reference is dynamic. The reference changes to always be the k-1 category. So in our model, right, the probability of 1 is going to be the cumulative probability, and the probability of 2 is the cumulative probability of 2 minus the cumulative probability of 1. And the probability of 3 is 1 minus the cumulative probability of 2, right? So we're going to have k-1 estimates here. And we're going to estimate the logit of that cumulative probability as kappa k. Kappa is going to be a cut point we estimate for each category in the model, minus 1, minus phi. And phi, I'm sorry, psi. And I forget which. That's theta. I am forgetting my Greek. I think that's theta. Too much Greek. Anyone want to correct me? Anyone know their Greek better than me? Yeah, anyway. I'm trying to just make sure I get my Greek right. This is totally unnecessary. It's a phi. Okay, so that's a phi. Kappa k minus phi I, where phi is going to be our linear model. Okay, and we're differencing it here because of the way we've set up the cumulative link. We're going to parameterize it this way, and it works. The linear model works the same as it always has. And then our priors. And of course, our priors are going to get messy here, right? Because we're estimating k-1 logistic regressions. So we're going to have priors for kappa. We're going to have k-1 kappa priors. And then we're going to have whatever priors we need for phi, right? Our linear model. Now, we can write it this way as a categorical model where our probabilities are spelled out this way. And we use this kind of we kind of use this cumulative function as we've done here, where we've defined the probability of 1 is q1, the probability of 2 is q2 minus q1, the probability of 3 is 1 minus q2. And that kind of bakes in that cumulative function into our model. Or we could write it as ordered logit and kind of remove that complexity. I've written it out here just to help us kind of think through what's exactly going in this model, that we're doing the stair-step approach rather than just the ordinary probability approach. But the ordered logit likelihood kind of assumes that model and uses the cumulative link function to reproduce it, right? Assuming that our categorical variable is translated into an integer or a factor that has the levels assigned to be 1, 2, 3, 4, 5 as appropriate, right? So we need to make sure we get those levels lined up appropriately. And you can see in our case, we have a 0, 1, 2, where the 0, 1, 2 are labeled unlikely, somewhat likely, very likely. So we've got that order structured appropriately. Okay. Then we can write in our model, right? So kappa is effectively an intercept for each level of the data, for each level of the outcome. So I don't need to put an intercept in my model anymore because I've already got these kappas that are going to act as cut points, right? You can see the way we set it up here. We have a logit of the cumulative probability is equal to kappa minus phi. So we can let kappa act as our intercept. And so I'm not going to bother with an alpha here because we've already kind of got one, right? I could add another in, but it's not going to contribute anything. I'm going to add a single beta where I want to look at the impact of GPA on, rated likelihood of saying you're going to apply to Graduate school, obviously, we had things like parents' educational attainment and whether it was a state or private school in the model, and those almost certainly matter too. We could imagine a more complex model here, but I'm going to stick to simple for now. And I'm going to use vague priors here, right? These are weakly informative. I don't know what the relationships are going to be, but they're going to, take on, the kind of full range of plausible values they could take, right? We're going to say like a 1 unit increase going from 2 to 3 GPA could increase the log odds of application by as much as -4 to 4, right? Pretty big change. Okay, so let's set the data up to estimate. Remember when I'm using RStan, I want to provide it only with those variables that I'm actually using in the model. So I'm going to make my slimmed down data frame. I want to add 1 to the apply variable, because remember the base number was 0 here, and I want it to be 1, 2, 3. Zeros sometimes have special meaning in Stan, so we want to be on a 1, 2, 3 scale rather than a 0, 1, 2 scale. It's currently a weird, because it's read in from a Stata data format. For any of you who have data in Stata, you can use the read. You notice here I use the Haven package, which is part of the tidyverse, and the read_DTA to read in a Stata file, right? So I can easily read in Stata files, but then these labels are kind of wonky, right? See here it says it's a double plus a label. So I just want to turn it into numeric. I could turn it into a factor too, and that would be fine. But I'm going to turn it into a numeric and add 1 to it. So now it's turned into 1, 2, 3. I'm going to take the apply and GPA variables out, right? Because those are the only two I'm going to model. I'm going to use the d-ord logit likelihood here, right? So that's part of the rethinking package. We can use the ordered logit density. Sometimes you'll also see these referred to as ordinal models or ordinal categorical models. Ordered logit, ordinal categorical, these are all the same, right? It's also just a special case of the multinomial where we're using that cumulative link function. But that's the link is already kind of baked in here. So it's actually pretty easy to specify. B is equal to B times GPA. B is normal 0.2. Kappa is normal 0.2. Pretty straightforward. So we do see a positive, right? The interval here is 0.14 to 0.82. So this is consistent with students with higher GPAs being more likely to apply or to say they're applying to graduate school. And our effective sample size in RHAT isn't great, but I think these models produce fine estimates. We might want to increase the number of iterations or improve things otherwise. These kappas are just the cut points. They're difficult to interpret on their own. And again, this is a model that's hard to interpret on its own. So we want to turn to visuals to help us understand what's going on. So I'm going to make 3 predictions. I'm going to let GPA range from 2 to 4. I'm going to have a 2 scenario. I'm going to have a 3 scenario and a 4 scenario. Right? So we have a 2.0, a 3.0, and a 4.0. And what do these students tell us about their likelihood of going to grad school? We're going to simulate using that data. So I'm going to get 1,000 predictions for 2, 1,000 predictions for 3, 1,000 predictions for 4. And I'm just going to rename it so that we can inspect it a little more easily. And what do we see going on here? So the book gives us a histogram we can make, but in this case, I think it's actually easier to just look at the output as a table, right? So for those students with a 2.0, very few of them said they were very likely to apply to grad school. 65 out of 1,000, right? Most of them said they were unlikely, and about 25%, 27% of the sample said they 26.7% of the sample said they were somewhat likely to apply. But as we go up, right, we do see increasing proportions. Those 3.0 students, more of them said they were definitely applying. More of them said they were somewhat likely. Fewer of them said they were unlikely. By the time we get to the 4.0s, most of the students said they were either somewhat or very likely to apply to grad school, right? So we see a really clear expected linear relationship here. And we also could, kind of pull out predictions for each group and draw posterior densities around them. And the nice feature here, this is obviously something we could have just done with a table without running a statistical model for it, but we've added the GPA predictor, and we could add additional predictors here and get some estimates of uncertainty as well. So these can be really useful models if you hit an outcome that's ordered categorical, right? In particular, if you're running surveys, right? And you're running surveys with thermometers or Likert scales or other kinds of things like that, where people are asked to rank their approval of a political candidate or rank their feelings about a particular policy. Ordered categorical models will become a very important part of your life, right? These are essential for that kind of research. Treating these as linear variables has some pretty big problems, and we should be skeptical of those approaches. Okay, so questions about these ordered categorical models? We're going through this material pretty fast. So, we're getting to a point with it where the math does get pretty tricky. The math for some of these other likelihoods is a little simpler to work with, but once we get to these mixed models, the math does get relatively complicated. So I do encourage you to make sure that you're keeping up with the reading, just to kind of give yourself another chance to think about what's going on under the hood with these approaches. But again, the goal here is you may never use some of these models. You're almost certain, if you do ever run a count model, though, over dispersion will be a part of your life. If you do ever work with survey data, then ordered categoricals are likely to be a part of your life. If you ever work with count data, zero inflation is almost certain to be a part of your life. I will give you a caution with zero inflation. People overuse it. You need to have a good theoretical reason for it. Don't just use it because your data has a lot of zeros. Use it because you can explain the process that turns the event on or off, right? Don't use it just because you have a count with a lot of zeros. It's entirely possible to have a count with a lot of zeros. But in the case of my police killings data, there were a lot of zeros. And, if I was just looking at that, I'm like, oh, that looks zero inflated. But all counties in the US have some kind of law enforcement present, right? There's no county where that likelihood is totally flipped off, right? So I would be hesitant to use it in that context. So think carefully about them. They're really useful for particular applications, but you do need to justify them clearly.
So the zero inflated, that's only when actually something can inflate the zeros because it's shutting off the option of it happening?
Yep. There's an event that must occur or must not occur for the process to kick off. In the book, McElrath uses the example of the monks producing manuscripts in the abbey, but some days the monks decide to go to the wine cellar, right? And on the days that the monks decide to go to the wine cellar, they're not writing anything. And so first we need to account for the probability that the monks are drunk and not writing, right? And so there's two processes going on. Did the monks drink today? Yes or no? If they did not drink, they were working. So if they were working, they produced manuscripts. Sometimes they'll produce zero when they produce manuscripts, right? So that's kind of one example. But I think, the example of there being, some contaminant in the water stream that killed off all the salamanders is equally appropriate. Or if we're in a county where there is no law enforcement and no one could have been killed by police because there are no police there, right? Or the example of how many doctor's visits did you take in the last year? Well, if you're uninsured, you're far less likely to ever go to the doctor in the first place because it's prohibitively expensive for you to go, right? So the probability of it being zero there is much, much higher because you haven't flipped on the switch that opens up the door to allow you to go to the doctor.
One more question. So if I'm doing this kind of model, and right in the very beginning we set up this model with a Poisson distribution, and if I thought, for example, my data will follow the gamma distribution, then I would set up something similar but with a gamma distribution instead of a Poisson distribution.
Sure. Yeah, in theory you could have zero inflation on any distribution, right? It occurs most often. I've never seen it with a gamma, but like the gamma Poisson, right, the negative binomial we introduced, you certainly could run zero inflation on that.
This is not with a zero inflation. This is just in general, if I want to do a model, but it's going to follow a different distribution.
Yeah, you can use any likelihood you want, right?
Right.
That's
So that's the
that's
same process would work for any.
yeah. Yeah, I mean that's kind of what I'm trying to tell you through the whole class, right? Is that, we often get stuck in just running the normal model for everything using an OLS, or I think most analysts will use some combination of only OLS, only normal model, and occasionally using a logistic model. But there's no reason for that other than training, right? The number of likelihoods you could use is potentially infinite. You could define any likelihood you want, right? You just have to make a case for it. And then kind of taking McElrath's guidance seriously, we also need to think about kind of principles that will help us select the appropriate likelihood, where we want to select the least informative likelihood that meets the restrictions of our data, right? Meeting that maximum entropy assumption. But yeah, I mean, there's a tremendous number of possibilities. If you the built-in GLM function into R, I believe, has 9 or 10 different likelihood families you can use, and a lot of different link functions you could use as well, right? The BRMS tool I'm going to show you at the end of the semester has, I think, 12 to 15 built-in likelihoods. But it is kind of very dependent on your application, and I do want you all to think creatively about kind of what is driving this process, what are the constraints of the data, and what likelihood makes the most sense. And there's no reason you can't try multiple approaches and kind of think through them, but the maximum entropy principles will help you kind of make that selection. In general, if you have a count variable, you should use a count model. It's more appropriate than a number that produces real numbers, because you can have negative counts and you can't have non-integer counts, right? And that the count model is just more appropriate, and it captures the dispersion process more appropriately. If your model produces a non-negative real number, then yeah, a gamma or an exponential is great, right? Depending on what you think the shape of that distribution is going to look like. Or a log normal, or there's lots of possibilities. Okay, other questions?
So like our last exercise that we did here, I'm just trying to wrap my head around like categorical versus continuous. This would not work with the salamander data, in other words. So
No.
Okay, all right. I'm just good thinking. Okay.
Yeah. No, that's a count. The salamander data from the homework was a count, and a count is an integer that is non-negative, right? So a count is 0, 1, 2, 3, 4, right? Now we have kind of translated this into a 0, 1, 2 framework, but a 3 or a 4 is not possible here, right? A categorical has a fixed number of categories, right? New categories can't emerge out of nowhere in this approach, and we're treating it fundamentally differently than we would a count, where we're asking the probability that you're in one of these groups. You must be in one of these groups, and everyone's in one of these groups. As opposed to count,
Okay.
Could be 0, could be 99, right? Yeah. But the thing about the ordered categoricals, right, is there's a fixed order to them, unlike a regular categorical, which has no inherent ordering to it. You like Coke or Pepsi or Sprite, right? There's no inherent order to that. Okay, so yeah, I hope this is the end of our GLMs unit, right? So we've kind of introduced a whole lot of tools. Before you had the single screwdriver. Now you've got like 15 different tips screwdrivers that you can use for different kinds of problems. They're all screwdrivers still, but they will help you solve different problems in different ways. And the goal here is to kind of keep adding tools to that belt so that you can solve an increasing number of problems. These mixture models are super, super useful for real-world processes. Real-world processes are very rarely work exactly as our likelihoods assume. Those assumptions are often, you know, unrealistic but not costly, right? Normality of errors with the normal model, symmetric distances. Like, do I really care about it? Maybe it's not going to affect inferences, but it's safer to go with the approach that best predicts out, or what, retrodicts the data. Best is able to recover, if I give it a likelihood, and I model the process, can it produce the data I observed, right? That's a really good challenge for a model. Can it produce the actual data? If it can't do that, and we have a distribution that can do that, why aren't we using the distribution that could actually produce the observed data, right? And that's a question you should be asking yourself, and you should also be asking your peers as you start to kind of move into, a position of evaluating quantitative research. Again, I can't emphasize it enough. Use over dispersion in your count models. Just assume they're over dispersed for the most part. They almost always are. You can, add the over dispersion in once you settle, and you kind of run some tests to make sure things are playing the way you want them to, but you should assume they're over dispersed. Okay, so if you want, the easy questions in chapter 12 are a good review of the content. Has anyone heard about the hurricane name paper, where hurricanes with female names are more likely to kill people because people don't? And so that paper was, published, got a lot of coverage, turned out to be absolute garbage. The stats in it were really bad, but there is a fun exercise in like hard 1 through 4 in this chapter. Actually have you replicate the analysis and figure out the problems with the analysis. So if you want to do that, it'd be a really great exercise in kind of testing your modeling chops. But I'm going to assign hard 6 as the optional hard problem for the week if you really want to practice with these models. But again, take as much or as little time with these practice sets as you have right now. No pressure, but good practice. Okay, and again on the labs, I saw everyone's feedback. Thank you. We'll cover, I think we should be able to cover just about everything on that. I'll start with user functions, user-defined functions on Tuesday. So we'll kind of work through how you can program your own functions into R to do tasks that you need to do over and over again. Like maybe you need to clean data in a particular way over and over again. Or maybe you want to do a math operation over and over again. We can write functions for that. I'll show you how to do that. And then I think the following week we'll do some advanced R Markdown. So I'll show you how to make really pretty documents in R Markdown. And I'll kind of walk you through my workflow. So I actually write academic papers using R Markdown, and I'll show you how you can do that if you want to. You can do citations, you can do advanced table formatting, you can do advanced graphics formatting too. Yeah, anything else? We're good? Okay, stay well, take care. Bye, everybody.